Hello students, and welcome to our second and final video of this week regarding ethers, epoxides, and thiols. So when we ended last time, we talked about how ethers and epoxides could be created. We've talked about various ways of creating ethers before and epoxides. Previously, in Chapter 8, we had talked about how to create an epoxide by reacting an alkene with a peroxy acid. And we saw a new way where we could do a halohydrin formation on the alkene with Br2 and water, for example, and then after that, treat with a strong base. Then we get the epoxide product. And so why do we want epoxides? Well, epoxides are highly reactive due to the fact that they have this three-membered ring with oxygen in it, like this. And so that means this angle here is very small, and that leads to pressure for this ring to open. And so that means if we have some nucleophile, and it will do a SN2 attack with this as a leaving group, especially if we protonate the oxygen, it would make a particularly stable leaving group. And so these are going to be useful as substrates in SN2 reactions with Grignard, with all kinds of nucleophiles like Grignard, hydride, alcohols, alkoxides. So let's take a look at that. Let's say, for example, we have a strong nucleophile, strong base like hydroxide. As I said, this ring is highly unstable, so it's easy to open. So we can actually do this SN2 without even protonating the oxygen. So usually when we want something to leave, we will need to protonate the oxygen so that when the leaving group leaves, it leaves as a neutral molecule, which makes it more stable. But this ring, this very narrow, this highly strained ring here is just ready to pop open. So the SN2 happens quite readily, even if we don't protonate the oxygen. And so the hydroxide nucleophile here attacks the oxygen, leaves as a leaving group, and then we have the negative OH group here, or a negative oxide here. We have the OH group attached, and at that point it needs to be protonated. So if this is happening in water as a solvent, there's plenty of water around, so it grabs a proton from water, leaves those electrons behind, and so you end up with a diol if you react this this epoxide with a OH, a hydroxide. And the opening of the ring here is favored due to the relief of the ring strength mentioning. So that allows this to go, even though we know that oxides like this, leaving with a negative charge, aren't great leaving groups, but it's still favorable because we're relieving that ring strength. So here, if you had just a standard ether and you were trying to do a substitution with hydroxide, it just wouldn't work. The activation energy would be huge. However, by having the ether in the form of an epoxide, at that point, it's starting at a much higher energy, activation energy much less, and so you can get to that alkoxide product much more easily. That's why we wouldn't use hydroxide as a nucleophile to react with the ether, but we could use it with the epoxide because it's a highly strained ring, making it much less stable than a standard ether. And we can do this with all kinds of nucleophiles. So we can have alkoxide ions, in which case we'll have the nucleophilic attack by the alkoxide, producing another ether. We can have other nucleophiles such as cyanide, thiosulfide, hydrosulfide rather. These are nucleophiles that would behave just fine. Any Grignard having a carbon as a nucleophile, a carbanion as a nucleophile, that works. Hydride ion, for example, coming from lithium aluminum hydride or sodium borohydride, also a nucleophile. So anything that's a decent nucleophile will react quite nicely with this ring-strained epoxide in an SN2 type of fashion to open the ring. And we follow up with water to protonate the oxide ion that leaves as a leaving group. So when it comes to regioselectivity, we're going to think about the regioselectivity in a similar way that we had in the past. When we were talking about, for example, bromonium ions, the mercurinium ion back in chapter 8. In terms of this reaction, it behaves like a SN2 reaction. And so when it comes to this SN2 reaction here, the nucleophile is going to attack at the less sterically hindered position. And so the nucleophile here, where there's no groups, it's very easy to attack. So the nucleophile can attack. At that point, ring opens up. This, we get the oxide, alkoxide, and then the alkoxide is protonated by the water. You get the alcohol. Now, when it comes to the stereoselectivity, just like it's basically an SN2 reaction, so you're going to get an inversion in the stereochemistry here. So notice that the nucleophile here is going to attack from the backside. It has to. So when it does, initially there was a bond between the carbon and this oxygen in the wedge position here. Now it's going to be the nucleophile attached in the dashed position, because again, the nucleophile can't attack from the top here, kind of like when we were talking about bromonium ions before in chapter 8. Same thing, it can't attack from the top, it has to attack from the back, so it's like SN2 style, and now the nucleophile is on dash rather than the wedge. So there is a stereochemical inversion here, and you're going to note that the hydroxyl group in the end is anti in position to the nucleophile that attacked. Now you can make the opening of the ring occur even easier if you protonate the oxygen first. And so if we react this with a hydrohalic acid, the first thing that will happen is a proton transfer protonating the alcohol, and that makes it a great leaving group. So when we have the nucleophilic attack, it leaves just fine, and at that point it's already protonated, so you don't need to follow up with water to protonate the alcohol. It's already protonated. We can open this ring under acidic conditions. It's even more favorable because we're not leaving as a negative ion, it's leaving as a neutral OH. So you don't have to use just a halide ion too. If you expose to an acid, you can use other nucleophiles. Weak nucleophiles like water or alcohols will work as well. Do the same thing. So if, for example, antifreeze, ethylene glycol, this is ethylene glycol, it's a diol. It's made industrial in this fashion, so we protonate the epoxide first, and then, we can have this, weak nucleophile will work just fine in that case, like water or alcohols, and then nucleophilic attack by the water. Let's take a look at the mechanism. We start by protonating the alcohol with the acid. This makes it a much better leaving group. So even bad, not great nucleophiles like water or alcohol will work at this point, because this is going to leave just even easier than that. This ring really wants to open. And so then we get the nucleophilic attack by the weak nucleophile water. That causes the ring to open up. Now this oxygen has 3 bonds, 2 to the hydrogen and 1 to carbon, 1 lone pair, so it has a positive formal charge. At that point, the water can come and deprotonate it, and then the acid is recovered. So the acid catalyzed nucleophilic attack here. Now, there is something a little bit different when you use protonate the OH though, because now what you've done is you've made it a much better leaving group, right? And also you have the positive formal charge on the oxide ion. Okay, so at this point there's something else to think about, and that is here when you got this oxide protonated, it's not just kinetics that are going to be in the kinetics of like the lack of a steric hindrance at the primary position. So there's going to be a competition now with another kind of stability of the transition state. And so if you have one position on the epoxide that is primary and one that is secondary, well, then the fact that it's clear for the nucleophile to attack at the primary position means that it will be preferred. But something else happens when you have a tertiary epoxide like this. The nucleophile in this case, when you protonate the oxygen, is going to prefer to attack here, and that's because you're going to have some carbocation character at that point. So it's similar. So here is really, really similar here to what we were talking about with the bromonium ion. So in the case of the protonated epoxide, now we've got a partial positive charge here. And in terms of where this partial positive charge is lying, it's going to affect the result of the nucleophilic attack here. So when we're comparing the primary position to the secondary position, the dominant factor here is the steric effect. The fact that there's a group here blocks the backside attack of the nucleophile. And so the nucleophilic attack happens much more readily at the primary position. However, when we're comparing to the tertiary position, it's the location of the partial positive charge that is more important. Because the epoxide is a cation here, the electronic effects result in a CO bond to the tertiary carbon that's weaker here, meaning that the positive formal charge is more nicely stabilized on this tertiary position. And so we don't need that bond to the oxygen anymore to share those, those electrons. And at that point, the dominant factor will be this electronic effect, making for a more stable transition state when the nucleophile is attacking at the tertiary position and the bond is breaking than at the primary. So that's a little bit of a wrinkle there. When you protonate the epoxide, now you've got this partial positive charge to think. At that point, the nucleophile will prefer to attack at the tertiary position. You can kind of think of it as having a kind of ish tertiary carbocation here, which is far more stable than a primary as a part of the transition state. So that's why it's preferred. So under acidic conditions, however, you're going to see the inversion of the configuration regardless of which carbon the epoxide attacks. Okay, so for example here, we've got a tertiary carbon, right? And the methyl group here is on the bottom, and we said, well, this nucleophile is still going to attack from the back side. And so what's going to happen here is this oxygen is going to go over here. So what, the nucleophile attacking, let's see, alcohol, it's an alcohol in this case. It's still going to be attacking from the back side. And then this is going to be opening up. So that's going to end up making your alcohol here on this carbon on the right here. But here, the attack's happening from the back side. So now there's no bond here to the oxygen. Methyl is going to be up here in this one. And the nucleophile that attacked is going to be on the dash position on the opposite side. So no change here, just a reminder that, before we were attacking primary carbons, we didn't really have to worry about this inversion of configuration. But here, if we're attacking a tertiary carbon, we really have to think about that inversion of configuration, just like we would expect here. And that's going to be the reactions of epoxides. Now we'll move on to thiols. So thiols are like alcohols, except instead of having a OH group, they have a SH group. And they're named very similar to alcohols, except instead of ending with all, they keep the E here and they end with thiol. So here this would be, if we numbered this 1, 2, 3, 4, so it would be butanol. The oxygen, the OH group's on the first carbon, and then there's a methyl on the third carbon, so 3-methyl-1-butanol. Now this is the same molecule, however, the hydroxyl group is replaced with a thiol group. And so we now call this, because it's 4 carbons, we say butane, and then we end with thiol. Butane, thiol. Put a 1 here because the thiol's on the first carbon, and then on the third carbon there's a 3-methyl. Now, again, there are some common names that are kind of entrenched into the language of chemistry. Thiols are often called mercaptans, and so you'll see that they'll just use Mercapto here as the prefix to name a thiol group, especially in the presence of another alcohol group here. So here we're calling it 1-butanol. We have butanol, 4 carbons on the main chain, hydroxyl group on the 1. We have on carbon number 3 a methyl group, and then we also have this thiol group, so it's called Mercapto, carbon 3 Mercapto. Here's a common name here, dimercaprol, common. This would be the IUPAC name, 2,3-dimercapto-1-propanol. Very common as a common name for this, used to treat mercury poisoning. In terms of properties of thiols, they smell bad. Your nose detects an SH bond as like poop, rotten eggs, skunk, that kind of thing. And so, for example, methane thiol, you know, gas kind of smells skunky too, right? Like natural gas that you cook with, because methane thiol has been added. So you're not really smelling the natural gas. What you're really smelling is the methane thiol that has been added to it. In terms of the deprotonated form here, the hydrosulfide ion. The hydrosulfide ion is a strong nucleophile and a weak base. So this can be used in substitution reactions. Promote a SN2 rather than an E2 because it's not a when it comes to the oxidation of sulfides, this is different than the oxidation of alcohols. So in the last chapter, we learned about alcohols. If you take, let's say, ethanol and you oxidize it with, chromic acid or something, or potassium permanganate, you will get a ether. You can oxidize it further, carboxylic acid. That thiols, it's different. With thiols, what happens when you oxidize is, remember how I told you one way of thinking of oxidation is removing hydrogen atoms, right? And that's exactly what happens. If you have 2 thiols, the hydrogen atoms are removed and you get a bond between the 2 sulfur atoms. And this is called a disulfide linkage or a disulfide bridge in the case of proteins. So there are amino acids in proteins that have thiols too. There's one particular amino acid and will create these disulfide bridges, which is important to the structure of proteins. I'm not sure what happened to my visuals here, but this is supposed to be a minus charge here. It's supposed to be a plus. Sure what happened to my symbols here, but this is a minus, this is a plus this, and so you can make a disulfide in this way. You can treat with a halogen like bromine, and you'll get a SN2 here with the bromine, and that will create a bond between the sulfur and the bromine. At that point, we have the nucleophilic attack by another sulfide here, and this one involves the loss of the bromine, and at that point we have a disulfide. We've oxidized the thiol and made this disulfide linkage. Disulfide linkages are super important to protein chemistry. Your hairs are strings of protein, and the curliness of your hair is locked in by these disulfide linkages. So if you ever go to have your hair chemically curled or straightened, what they'll do is they'll expose the proteins in your hair to a reducing agent. They will reduce it and make the separate thiols, and then they will put your hair in the position that you want it, like with curlers or with the things to flatten it, and then they'll oxidize again and reestablish new disulfide bonds, and then your hair will be chemically changed in order to preserve that configuration that they put it in when they did oxidation to create the disulfide linkages again. So these bonds are pretty easy to break. You can break them and then remake them, change the way your hair is curled. That's the way it works. Make it either curlier or straighter. That's what they say when they say a chemical curl or chemical straightening. That's what I'm talking about. When it comes to sulfides, when they're oxidized, they can also be oxidized to sulfoxides or sulfones here, which are like substituted sulfates basically with R groups here. So depending on the oxidizing agent you choose, you'll either make sulfoxide or a sulfone. In addition, sulfides they're quite readily oxidized. They're very easily oxidized. So you can use DMS, dimethyl sulfoxide, to reduce ozone, and then you'll have a similar to the ozonolysis here, where you'll break what we're interested here is the byproduct, the DMS here. And when we oxidize it, we break this one, as we saw with a 2 carbonyls, but we also get the DMSO produced as a byproduct here. That's how we can get the dimethyl sulfoxide. Now, so those are your thiols and sulfides, and that's the extent to which we're going to cover thiols and sulfides. Your book does go into some more detail, but that's the most that I'm going to. That's as deep as I'm going to go with thiols and sulfides. And so finally, the last bit is we've got a few new reactions in this chapter, so we should think about how we can use them. So if we use a peroxy acid like MCPBA on an alkene and we make an epoxide, then we can use that epoxide to do a nucleophilic substitution. This is going to be particularly useful if you're trying to make a product that has 2 adjacent functional groups, one of which is a hydroxyl group and one of which is another nucleophile. So for example here, if we saw this, our synthesis required us to produce a product that has an OH group that is right on the carbon right next to this cyanide. Well, we know cyanide's a great nucleophile. So if we made this into epoxide, let's say by using MCPBA, we could also say that's a more specific, or we can just say RCO3H, whatever. We'll get the epoxide, right? And then we follow that up with the nucleophilic attack by sodium cyanide, and then finally we'd have to protonate the alcohol, so then we can water at the end. And there's more than one way to do this. That's one way. Yeah. So that's one way we can get. So the big tip off here is when you see the OH group next to some other nucleophile on the neighboring. If we react with an epoxide of the Grignard reagent, we can increase the carbon skeleton. So we know we have 2 moves now to increase the number of carbon atoms, either the alkylate ions or the Grignard reagent. So if we react a Grignard reagent with an ether, it will behave as a nucleophile, and then we can add on whatever group. And again, this will be the nucleophile and the neighboring carbon to the OH group. But this will add on carbon atoms. So if you want to add on carbon atoms, one way to do it is to do a Grignard reagent with a epoxide, and this will be particularly useful if your final product involves additional carbon atoms neighboring to the carbon with the OH. So in terms of the epoxide that's produced, here in the case of reacting with an epoxide, we've added the 2 carbon atoms that were a part of the epoxide. So we end up, remember, when you're counting your carbons, you have to keep in mind that the epoxide itself has 2 carbon atoms, and then whatever your Grignard reagent is, which is shown as the R here, has more carbon atoms. So that's something to think about when you're thinking about how many carbon atoms do I want to have on here, right? So here, for example, in this case, if we react, if we have our Grignard reagent and and we're reacting it with a Grignard reagent, we're going to get those whatever carbons were on the original carbonyl group. So this carbonyl had 2 carbons here, and then we added the R group. Whereas when you're reacting with epoxide, we had 2 carbon atoms here, and the R group now is on 1 carbon away from the O, rather than the 2 carbon atoms being here. So depending on how you want to do it, what your product is. If your product ultimately is a bunch of new carbon atoms 1 carbon away from the OH group, then producing the epoxide and then doing a nucleophilic attack with the Grignard is the way. However, if you want the additional carbon atoms to be on the same carbon as the OH group, then you're going to want to do the Grignard reaction on a carbonyl instead of an epoxide. So you see in this case, the R group now is attached to the same carbon where the opposed to made this same situation, but with going through an epoxide. So that's something to keep in mind for synthesis problems as well. So here's an example. Let's think about what we want to do. Consider the reagents necessary to accomplish the synthesis. And so when we look here, our Grignard, we can make a Grignard if we use magnesium here, make the Grignard. We're going to get essentially this. It's negative, are positive. So we got our Grignard now, and now notice that we're attached to the carbon that is neighboring the OH, which tells us we probably want to go through an epoxide intermediate. In this case, that will make it easier. And so we introduce our epoxide, 2 carbons here, and there's one more carbon on it too. So this is the epoxide we might use, assuming we're allowed to use it. And we have primary versus secondary, so the nucleophile is going to attack at the primary position in this case, because the other one's secondary. So go right there, then this will open up. And so then finally, we want to treat with water, because at that point, I'll just do that as a separate step here. You can show it all in one step too. At that point now, we have this attached, we have this guy, we have this, and this is the deprotonated oxide that's still there. So we're now treat this with water to protonate the oxide, and then final product here. Or we could use acid to protonate it. Water would be fine too. And so the take-home message here was we used the epoxide with our Grignard because that installed all the carbon atoms from our Grignard on a carbon neighboring the OH, rather than to be the case if we had a carbonyl. And so those are the kinds of things to consider when performing syntheses with these. And these are the reactions of ethers and epoxides. So and a little bit about thiols and ethers. So thank you for joining me for this video. That'll be it for this week. Only about an hour worth of videos for this last week of the Chem 212. Best of luck in your studying. Let me know if you need help, and best of luck on the final exam. Go, go, go. I'm cheering for you. Let me know if you get stuck while you're studying. Have a